Good afternoon, my dear students. Today I am going to discuss about mean value theorem. In the last class, we have discussed the Rolle's theorems and solved some few problems. Let us revise what is actually statement of Rolle's theorem, what is its geometrical interpretation again. So what actually Rolle's theorem is? The Rolle's theorem is if a function defined in a closed interval b, it means it is a real valued function satisfying the condition. First condition is it is continuous in closed interval b, it is differentiable in open interval b, such that functional value at the end point in the closed interval is equal. Then the theorem says there exists a real number c between a and b, that means in the open interval ab, such that f dash c equal to 0. There exists actually at least minimum one point between a and b in the open interval ab, such that f dash c equal to 0. F dash c means what? Slope of the tangent at the point c, which is equal to 0. So geometrically you can say that the tangent at the point c is parallel to x-axis, since the slope of x-axis is what? 0. And since f dash c equal to 0, slope of the tangent f dash c, slope of the x-axis is 0, and both are same. So from here you can conclude that what? At the point c, tangent is what? Parallel to x-axis. Or for x is equal to c, there will be a y coordinate that is called fc. And finally you are getting the point. This is the point on the curve. What happened? Where tangent is parallel to x-axis. Geometrically you can say that the Rolle's theorem tells us between the point, suppose this is a and this is b on the curve, there exists at least one point CFC where what happened? Tangent is parallel to x-axis. This is the geometrical interpretation of Rolle's theorem. So last class we have discussed few questions related to this particular theorem. So today we are going to solve few more problems related to this particular Rolle's theorem. So let us start with a problem. First problem is verify Rolle's theorem. Verify Rolle's theorem for the function. Verify Rolle's theorem for the function fx equal to 3 plus x minus 2 all to the power 2 by 3, where x belongs to domain of the function is what? Closed interval 1, 3. So you have to check whether this function, Rolle's theorem is verified on this interval or not. So you know the condition of Rolle's theorem. First we find C, what is f dash x? F dash x is equal to what? It is 0. It will be x 2 by 3 into x minus 2 whole to the power 2 by 3 minus 1. You can apply the formula x to the power n into x to the power n minus 1. And since it is not x, again derivative of x, it will get 1. Finally 2 by 3 into x minus 2 whole to the power minus 1 by 3. And finally you get 2 by 3 into 1 by x minus 2 whole to the power 1 by 3. So this is your f dash x. Now in this interval you have to show that in this open interval the function is what? Differentiable. So you consider a point in this interval, that is 2, between 1 and 3, and you see if you put then what will be f dash 2? If you put x is equal to 2 here, what you will get? You will get 2 minus 2 over to the power 1 by 3, and which is actually undefined, or you can say infinity, which is undefined. 2 minus 2 is 0, denominator becomes 0, it becomes 1 by 0, and finally f dash 2 is what? Undefined. Okay, so that is fx is not differentiable at x is equal to what? 2. And since in a particular, within this interval, in a particular point, the function is not differentiable, so you can say that throughout this interval, the function is not differentiable. That means it is not satisfied the condition of one condition of Rolle's theorem. The condition is that the function is much differentiable in this open interval. In this open interval means in every point in this open interval. Since 2 is a point where the function is not differentiable, therefore you can say that Rolle's theorem is not valid for this function on this interval. Rolle's theorem is not valid. So Rolle's theorem is not verified. Valid means what? We can say not verified. Okay. So this is the way question may comes. Sometimes what happens, you have to check whether this function is differentiable in this open interval or not. You have to check it, and then finally you go to the other condition and then check all the condition of Rolle's theorems are satisfied or not. Here in this a particular condition is not satisfied, and hence we conclude that Rolle's theorem is not valid for this particular problem. Okay. So moving ahead with another problem, another questions. The next question is, using Rolle's theorem, find the points on the curve fx equal to 4 minus x square, x belongs to minus 2, close interval this. Find the point of the curve fx equal to where tangent is parallel to x-axis. Tangent is parallel to x-axis. This is a nice question. See, that means what happened in your Rolle's theorem, what this is, suppose that for this particular curve, tangent is parallel to x-axis, is FA, this is FB, okay? Between in this closed interval AB. So you have to find a point C, FC on the curve where tangent is parallel to x-axis. That means first you find the point between A and B where what tangent is parallel to x-axis, and for particular C you have to find the corresponding points FC on the curve, and finally conclude that this is the point where tangent is parallel to x-axis. So first you see whether the conditions are satisfied or not. Given function is what? If you differentiate, you will get, you consider this is your x, and we know that TTS of root x is equal to what? 1 by 2 root x. So it will be this type. Using chain rule, since this is not your x, so again derivative of this part will be what? Minus 2x. 2 to cancel, it will be minus x by root over 4 minus x square. Okay. Now f dash x is equal to this one. Clear? Clearly you see, clearly fx is differentiable in open interval minus 2 to only what when x is equal to minus 2, f of f dash minus 2 is undefined, and when x is equal to what plus 2, again it will be 0, and what happen f dash 2 will be undefined. But for all other points between minus 2 and 2, what happen, you will get f dash x an unique value. So you can say that the function is differentiable within this open interval except minus 2 and 2. Okay, and since we know that if a function is differentiable, then it is also continuous. So since fx is differentiable in this open interval minus 2 2, so it is continuous in also, it is also continuous in this open interval. So our job is to show that the function is also continuous in this closed interval. Okay, minus 2 to 2. Since it is already continuous in open interval, from the definition of that a function is differentiable at a point, then it is continuous at that point. Since it is differentiable in open interval minus 2 to 2, so it is continuous at the open interval minus this open interval. So our main aim is to show that at the end point minus 2 and at the end point 2 whether the function is continuous or not. If it is continuous, then we can conclude that the function is continuous in the closed interval. Already it is continuous in the open interval. So हमें क्या करना है, ओपन एंड पॉइंट में कंटिन्यूटी चेक करना है, एंड एंड पॉइंट में कंटिन्यूटी चेक करके हमें कंक्लूड करेंगे कि दिस इज कंटिन्यूअस इन द क्लोज इंटरवल. नाउ at x is equal to 2, limit x tends to 2, I am taking last limit x tends to 2 means here left hand limit and right hand limit I am including together, is equal to limit x tends to 2. What is fx? Fx is equal to root over 4 minus x square, and if you put x is equal to 2 here, you are getting what, 0. And also you see in your original function f2 equal to what, 4 minus 4, root over 4 minus 4 is equal to what, 0. So you can write this is equal to what, f2, and which is the definition of that, limit x tends to a, fx is equal to what, fa, then the function is continuous at x is equal to a. Since limit x tends to 2, fx is equal to what, f2, therefore f is continuous at x is equal to 2. Now we have to check at x is equal to what, minus 2 also at x is equal to what, minus 2, limit x tends to 2 minus fx, I'm sorry, x tends to minus 2, x tends to minus 2, the function is what, 4 minus x square, and again you put x is equal to minus 2 here, you are getting what, 0, and which is nothing but your f of minus 2. If you put x is equal to minus 2 here, f of minus 2 equal to 4 minus 4 is equal to what, 0. So again by the definition f is continuous at x is equal to minus 2. So since already the function is differentiable at open interval, so it is continuous this open interval, and now we conclude that at the end point also function is continuous. Therefore we can write fx is continuous in minus 2 to 2. So first condition is satisfied, second condition of Rolle's theorem is satisfied. Now what is the third condition? Third condition is the functional value at the end point of the closed interval should be equal. Also it is obvious f of 2 equal to 0 equal to what, f of minus 2, we already show it, f of minus 2 equal to 0, f of 2 equal to what, 0. Therefore, all the conditions of Rolle's theorem are satisfied. All the conditions of Rolle's theorem are satisfied. Therefore, by the Rolle's theorem, therefore, there exists some C belongs to the open interval -2 to 2 such that f dash C equal to what? 0. So our job is to find what C now. Your f dash x was minus x by 4 minus x square. Then what will be f dash C? Replacing x by C. So f dash C will be minus C by root over 4 minus C square equal to 0 implies minus C equal to 0 implies C equal to what? 0. Now you have to check where this C equal to 0 lies in your open interval on given in open interval. This is the open interval. It should be. So we have taken some C belongs to this. Yes, 0 is belongs to what? -2 to 2. So it means that Rolle's theorem is verified. Rolle's theorem is verified. Okay. Now our aim is to show that at what point on the curve, that is tangent is parallel to x. F dash C equal to 0 means what? Yes, C means 0. So f dash 0 equal to what? 0 means what? At x is equal to 0, slope of the tangent is 0. Okay, means we know the slope of x-axis is 0. This is the slope of the tangent. Both are same. Means what? At x is equal to 0, the tangent is parallel to x-axis. Tangent is what? Parallel to what? X-axis. Okay. Now when x is equal to 0, then f0 equal to 4 minus 0 equal to what? 2. Understood? So finally, therefore, the tangent is parallel to x-axis. Yeah, sorry, you're right. Therefore, the point 0, 2 on the curve, you have to find the point on the curve where tangent is parallel to what? X-axis. Tangent is what? Parallel to what? X-axis. This is the point on this particular curve. Your curve is what? Fx is equal to what? 4 minus x square. On this curve, at the point 0, 2, the tangent is what? Parallel to what? X-axis. Tangent is what? Parallel to what? X-axis. Okay. So I hope you understand. So this is another way to find where the tangent is parallel to x-axis, on what point on the curve tangent is parallel to x-axis. This is one of the application of what? Rolle's theorem. So another problem I am going to solve today, that is a little different problem, interesting one. Question is, f is a function defined from closed interval -5 to 5 to r is differentiable, and if f dash x does not vanish means not equal to 0 for all x belongs to what? -5 to 5. That means what happened? The f dash x not equal to 0 within this interval. Then prove that f of minus 5 not equal to f of 5. This is given. That means if f dash x not equal to 0, that means not vanished in anywhere in the domain, so at the except the endpoint, then what happened? You have to show that this is equal to this. Clear? So in such type of problems, first we assume that using the contradiction method, assume that f of minus 5 equal to, or suppose that these are equal. Okay. Also, again, and your function is what? F dash x. The fx is what? Given fx is a differentiable function. Since fx is a differentiable function, therefore fx is continuous in closed interval minus 5 to 5 and differentiable in open interval minus 5 to 5. Since it is given that in your question it is differentiable, so a differentiable function is always continuous. So it is continuous in this closed interval and differentiable in open interval. So the condition of Rolle's theorem, one condition is that continuous, another condition is differentiable in this open interval, and third condition we assume that these are the three conditions of Rolle's theorem, and this particular problem is satisfying this question, this function fx satisfying all the three conditions. So by Rolle's theorem, there exists some c belongs to the open interval minus 5 to 5 such that f dash c equal to 0. So रोल्स थ्योरम कह रहा है कि ये जो दोनों ओपन इंटरवल के बीच में मिनिमम एक पॉइंट होगा, एक हो सकता है या ज़्यादा हो सकता है, सम पॉइंट है such that f dash c equal to 0, that means f dash x equal to 0 for some c in this domain. But in your question, what is given? The function is not equal to 0 for all x belongs to the domain. Okay, here you can say this closed interval. Okay, for all x belongs to the domain. Clear? And here we are going to show that f dash c equal to 0. That means we are telling that f dash x equal to 0 for some c. This statement is contradict with the given condition. Understood? So this statement contradict with our given condition. Why contradict? Because of our suppositions. We suppose that f of minus 5 is equal to what? F of 5. Therefore, we can conclude that this particular statement contradict with our given conditions. Hence, we can conclude that our assumption is what? Wrong. Our assumption is what? Wrong. So, what actually? It will be f of minus 5 not equal to what? F of 5. So, we can write like that. Therefore, which next line that which contradict that f dash x not equal to 0 for all x belongs to this. Okay, hence our supposition is wrong. Our supposition is wrong means what is the conclusion? That is, therefore, f of minus 5 not equal to what? F of 5. Hence proved. So this is another way of solving problem by using Rolle's theorems. So you can, in a different manner, question will be asked. So it is how you understand the problems and how to use the rules theorem in this problem to complete your answers. So very interesting problems are there. You will go to your text, find more problems and practice these problems. You will get an idea how to apply rules theorem in these problems. So in this rules theorem you can get, so the statement of the problem sometimes asked in the question in the examinations, and question also asks what is this geometrical interpretation. So you have to must know what is geometrical interpretation means. By rules theorem says there exists some point C within this open interval such that on the curve C FC, on the curve C comma FC, there exists at least one tangent which is parallel to what? Parallel to what? X-axis. This is the geometrical interpretation. Another way what happen, you can apply the rules theorems and solve the numericals. You can find the points on the curve where tangent is parallel to x-axis. So this is the application of Rolle's theorems, and a very interesting one. In the next class I will start with Lagrange's mean value theorem, and which is in short written as LMVT. LMVT means what? Lagrange's mean value theorem. There are two types of mean value theorem. One is what? Rolle's theorem. Another is what? Lagrange's mean value theorem. So the next topic of my next class is Lagrange's mean value theorem, is geometrical interpretations, and how we can use this Lagrange's mean value theorem to apply in equations. Okay. Also, I will discuss that Rolle's theorem actually a particular case. It is a particular case of Lagrange's mean value theorem. Lagrange's mean value theorem is satisfied for all, and that Rolle's theorem is a particular case. So thank you. I understand that. I hope that you all understand. Thank you very much. Thank you.